Jogamin. Last video, part 3 out of 3. What? Wait, yeah, probably. Part 3 out of 3 for derivation of parallel, moment of inertia. Yeah. This time we're, oh shoot, that's from last video. Wait. Okay, so, our next shape, or last shape, is a cylinder. Now let me tell you something, your skill in deriving moment of inertia for certain shapes depends on your knowledge of these shapes. You should be able to integrate and find the values. It's just that you don't know how the shape. If you don't know how the shape interacts in the 3D, bro, then you're probably cooked, bro. Come on. Hold on. What the hell is? Okay, so we're doing a cylinder. This time around, I'm gonna do it in the 2D. I haven't done it in the 2D, but let's do it in the 2D and let's see if it's equal to the. If it's equal to the 3D. Alright, so what I was thinking for the 2D version of cylinder is just a circle. Yeah, I know, crazy. And instead of a normal cylinder, right here, we're gonna have a hole in it with a radius r, alright? Staging finance. And this hole can be represented like this. Building. Can be finance. Let me start it. Okay, radius. I got a little donut action right here. Alright, assume this is in the middle of the thing, yeah. Okay. So this is this is always this part. Anyway, so let's define this radius r, big R, and then this small radius r, small r. Okay, so though this is technically a hole, we're gonna assume that this has area, and we're just subtracting it from this bigger circle. All right. So, oh shoot, it's bad. So for our equation, we're gonna use r prime instead. R prime dm. R prime dm. Yeah. And our bounds. Well, I'll tell you our bounds once I set up everything. So, dm. What is it equal to? Uniform density. Little sigma. It's gonna equal that little sigma, the area of the circle. Oh, which circle is it? Actually, oh wait, no. This is the density of the donut, not the two circles. Right? So, this thing is gonna equal to mass over area, where the area of a circle is pi r squared. But here's the thing. This isn't this r right here. We're gonna define it as r big R minus little r squared. Wait, I don't know where I stopped off at, but I had made a mistake here. So it is not r minus r squared or whatever. It's r squared minus r squared times pi, because the area of this thing is pi r squared, and the bigger circle is pi r squared, and the whole area of this is just a difference. So yeah, anyway, it's pi r squared minus r squared. And okay, so we're trying to expand outwards. We're trying to expand outwards. I'm going like schizophrenic. Okay, so dr is pushing outwards. So my little drawing. Yeah, so this is the density. It's or dm. Dm is a little circle, and here's the density of it. It's right here, and dr pushing out. So that means we need the circumference of the circle, because that's what's pushing out. So circumference is 2 pi r, which is actually, hold on, surprisingly, since we're using this circle as reference, it's actually the same r as this. So let me show you. 2 pi. Also, by the way, cancel out this 2 times. Well, it's 2 pi r. Yeah. So now it's integral r cubed dr. All right. So that r, where I got the circumference of this small circle, is actually the same r as this, and our bounds will be r to r. Wow. Can I define r as something else? So I can specific. Wait, no, yeah, because we're finding the area. When we're integrating, finding the area of this portion, so we should start from r and at r. Yeah. Yeah. Okay, makes sense. It's r to the 4, 1/4 times 2, so that's 1/2. R squared minus r times r to the 4, r to r, so that's just equal to r4 minus r squared. Over 2 times r squared minus r squared. And if you know your stuff, you can turn this into r squared minus r squared times r squared plus r squared. Cancel these out, and what you're left with is r squared plus r squared over 2, where this works if it's just a normal cylinder without this hole. If this little r is 0, that would just be r squared over 2. Oh yeah, I forgot math. Yeah, there you go. Okay, do I really want to do it in 3D now? It's the same process. In fact, you see the same numbers there. Well, we have a couple minutes, so I guess we do it. Yeah. So here I go cylinder. Just my copy. Yeah. Okay, and it's rotating around the axis. Runs on axis. So that. Okay. Essentially the same idea, really. Okay. I did this same integral, but I'll show you how we got there. So, this is h. little r, not even gonna write it. Maybe I will. Nah, it's too small. R? R. So, again, DM. What is DM? Well, it's this whole, the whole thing. Alright, so, DM equals DB. Wait, last video when I went to DB, did I even do it to DB? And if I did, wait. Guys, check for me if in the last video I went 3D. I don't remember going 3D. Wait, I think I did, but I just skipped over the volume part. Wait, did I? Yeah, I think I skipped over the DB part. Whatever. Anyways. Okay, this is like a omega skippable part. As DB equals. Wait a minute, hold on. Right, look. This DB considers we're pushing this way in the volume. We're finding the volume increments right when we push outwards. So here's the thing. This little inside thing right there, right here. Let's draw right here. So this shape right here is technically all air. Like this inside is really just air. So its real volume is a slight dr this way, but it's very small. It's dr small, right? So this is more or less just a ring, really tiny slick ring. And as we integrate and push this way, this ring will become the shape right here. That's what we're doing, right? When we push outwards and get more mass, it's gonna become the actual cylinder that we want, right? So that would mean, skippity twit. So this is dr. And this shape that we're pushing outwards is actually, it's not pi r squared. It is not pi r squared, This is not pi r squared, height. Because this is empty area. We are not considering this area here. We're considering the area that will have after it pushes outwards. So this is not right. What's really right is, okay, so to get the shape of this ring, and by extension, let me explain to you, like, if you roll this out like toilet paper, it would look like this. Like, you cut incision right here and then roll it out, it would look like this. And I finished it. So, this thickness dr with a height of h and circumference or length of 2 pi r. And remember, dr is like extremely small, so like, yeah. So that's the real area we're finding, not the inside volume. It's technically not even a volume, because this is what I forgot to show you on the last part 2 of the video by addition on part 1, when I drew a cube. But then, what we're actually doing is pushing a cube or a 3D shape that looks like this way by dr. That's kind of what we're doing here. We got a 2D shape and we're pushing dr to give it its thickness. So, given this knowledge, dB equals 2 pi rh dr. And then rho equals mass over volume. Well, that's just pi h, right? H, yeah. R squared minus R squared. That again, yeah. So with that, when we combine these two cancel out, and the r makes it to r cubed with the 2 dr, and we're back with what we had earlier: r squared minus R squared to r cubed dr. So I'm not showing you the math. It's the same equation before. Let me see how far I can go. Yeah, I can go that. Nice. That's the end of the video. I have to do this.